fine. Let's get started. Last time we talked about the Hawking radiation. So the essence of Hawking radiation is that you can always so short shield, black hole. Okay, so then the phi out is something like this one. This part is roughly can be written sum of alpha and phi in plus beta phi in star or something like that. And then of course there's a mode expansion in and out. Okay, and then whatever maybe J what I'm doing here, sorry, IJ, J, IJ, and J, and J, and then so in is the measured in phi in here, and phi out here. Okay, so they are related to two. There is a two mode expansion, and then if you just compute n of the which one? So vacuum, the vacuum in vacuum, and this is out one numbering operator, and in this is given to sum of again beta ij square, sum of beta ij square, I and j, and then this one is proportional to this sum radiation, some constant, and e to the omega over kappa. Surface gravity, kappa 2 pi, I don't remember the detail, minus 1. So this kappa is the Hawking temperature is given by kappa over 2 pi. Oops, sorry. So the to find this in the form of beta, we did lots of analysis in the last time, but the essence is the really one essence is just a mode expansion here and here has some have the different bases. So therefore, you have to write down this expansion coefficient, different Fourier modes. So therefore, you have to do the base change, so that when you do the computation of numbering operator in here, and sandwiched by in vacuum state, and then you have this amplitude, and then if you do the like a tedious computation to compute the beta, what you get is this kind of thermal radiation. So that's what we did last time. So essence is almost the same as this Unruh temperature, Unruh effect. It's Unruh. So yeah. So this is semi-classical calculation. Okay, and then since the black hole, so you just black hole, you have a black hole, and then it has some radiation. So this has energy. This take out energy. So the black hole is no longer black. Somehow, at least the semi-classical, I just do the thermal radiation. Semi-classical means that we just fix the background of the black hole geometry, but do the quantum field theory on the fixed background. Okay, so that's what I meant by semi-classical. And then so it's no longer black hole. It's no longer black if you apply the QFT in Hilbert spacetime, and the energy will be taken by thermal radiation which is roughly speaking some minus alpha a t to the fourth. So this is the Stefan Boltzmann law. Boltzmann law. Rho. Okay. So, and then yeah. So the dm is just dt is roughly speaking minus m squared. So the mass will reduce inverse square proportionally to its own mass. Okay. Fine. So that's the case. So therefore, so after some time, so the black hole will evaporate, and often people just write down like this kind of Penrose diagram for the black hole. I don't think Penrose diagram is something like so you have a singularity, but the Hawking radiation will take out the energy, so therefore, so at some point there is a Hawking radiation. So maybe I should use Hawking radiation will just come out like this way. I mean, it depends on how you write, but Hawking radiation after black hole can evaporate due to the summer radiation, and then it becomes black hole evaporation. So at some time, so the lifetime is some, roughly speaking, the proportion to m to the cube, and it's super long time. It's even if the mass of solar mass of the size of black hole, which is the solar mass, will take a huge amount of time. I don't know how long this one. Anyway, huge amount of time. But if you just keep applying this Hawking argument, black hole can evaporate. Okay. And then the important thing is that the so first information paradox. So today, the first half of the lecture is talk about information paradox. And then later, I will move on to black hole perturbations, which is called quasi-normal mode. So today's half of the lecture is black hole evaporation. Information paradox, which is too famous by Hawking. 1976, as far as I remember, something like that. Proposed by Hawking, and people still keep working on like after almost 50 years. Oh, it's kind of amazing. Half century before, people keep just obsessed on this problem. So I think I should talk about it. So okay. By the way, so this week I was have been very busy. The lecture note is not complete yet. It's really incomplete. So I will update it later. So, but today I'm going to talk about something which is not written even in the lecture note. So everybody is the first explanation of the Hawking paradox, which is written anywhere in the even popular book, is that so you start with the S wave, the very heavy S wave. S wave is like a S wave state psi. S wave is like the mode which can only change the radius direction, and it shrinks to the shrinks and they create some very tiny black hole. Let's consider such a process. Gedanken. Of course, this will never happen in reality, but as a Gedanken experiment, one can consider such a thing. And this black hole, if you apply the Hawking's argument, this will do the thermal radiation. So by the way, so this is pure state. I'm going to explain what the pure state means. later. And then after that, you have, after black hole evaporate, then you only have the some radiation at the infinity, whatever. Some radiation is left, and this is it's often write down the sum of e to the beta h n en and en like this way. So this is called mixed state. I will explain what the mixed state means. In basic. So anyway, so this kind of like a quantum information theoretical quantum mechanics is not usually taught in a school actually, people. So I will explain. So this, but according to quantum mechanics tell you that the time evolution is only like this way, Th psi. So H is Hamiltonian of the system. So this is still pure state. Pure state. So this is it's called unitary evolution. Time evolution, according to quantum mechanics. So this will contradict with the, so pure state and mixed states are different. This will really contradicts the law of quantum mechanics. So immediate contradiction. So this is any even popular book is written. This is one explanation of that. But there is something. So last time I talked about the. So the entropy is something like total entropy is the S black hole plus S outside. So it should be considered as a total system. So for instance, yeah. So if you just have the whatever. So you have a black hole, but you can just throw away some matter into the system. Into the system, if you throw away some matter in the system, the black hole will become fatter like this, right? And the entropy will increase. So therefore, before the matter enter and after matter enter, to have the consistent result, to have the consistent in the thermodynamics, so the delta S, this is the second law of thermodynamics. To save second law of thermodynamics, you have to consider the total system. Like this way. And then again, the same thing happened for the how to say, Hawking radiation. So first you have a black hole. If you create a black hole, have an entropy in which is the A over 4. But if you evaporate, everything becomes the thermal radiation. Thermal radiation. And the entropy will be just restored by this S outside. Okay? So therefore, if you consider the S total, should be like this. But now, page show that the quantum mechanically. So this is called, I will explain what the meaning of it. This is called coarse-grained entropy. Grained entropy. Coarse-grained entropy. But if you just consider so-called fine-grained, instead of this one, to really solve the information paradox on the page, I don't remember. Sorry, I don't even cite his paper. So page, I think, as far as I remember, 90, and also so 2000. Page mentioned that to really address this issue of information paradox, we need to consider fine-grained more quantum mechanical entropy. Fine-grained entropy, which is called, which is actually nothing but a so-called von Neumann entropy. Von Neumann minus trace of rho log rho. Rho log. So the page mentioned that which consider fine grained. I will explain what the fine grained entropy means. So the coarse grained entropy is the, I will explain both of them. What's the meaning of coarse grained? It really obeys the second thermodynamic law. But on the other hand, the fine grained or von Neumann entropy, whatever you call it, depends on the system you consider, it can decrease. And the page mentioned that so if you consider this fine grained entropy, so S von Neumann, and like this is a time, as I mentioned. So I explained, so this thermal radiation will, how to say, this is the time of black hole, time of black hole. So this is the lifetime of black hole. So at this point, the black hole will evaporate. So this should keep growing. So this is the S radiation. But on the other hand, as black hole, due to thermal radiation, the area shrinks. So therefore, the S black hole should decrease. And then at this point, it goes to 0. And then this fine grained entropy, indeed obey like this way. Like this way. So this is called page time. So I will explain why this has to be the case. And this should be the case. And the Hawking calculation of this S radiation keep growing till the black hole evaporates. After the evaporates, it just becomes constant. But if you consider fine grained entropy, this yellow curve should fine grained entropy should obey as a total system should obey this yellow curve. So therefore, there's something wrong about the Hawking calculation at the later stage of the black hole calculation. So that's what the Page proposed in the, I think, 90s. As far as I remember, I will cite his paper later. So this is a more refined version of the information paradox proposed by Page. And many people mention, for instance, Adi Strominger at Harvard. He's a super expert on the black hole. And then his student is actually at the CEMIS, Slava Lizov. And he told me that Adi Strominger always mentioned that to have if you have a consistent quantum gravity, consistency of quantum gravity, this quantum gravity, okay, QG, should explain this Page curve from first principle. From the first principle. So that's the another so more refined version of information paradox. So this is the first version is always mentioned in the anywhere when you talk about the information paradox, but a more refined version of the information paradox is this one. So that's the the first half I'm going to explain today. Anyway, so we reached to the Hawking radiation. At least I should talk about the information paradox. Otherwise, as a course, it's too strange. So. Okay, to address this issue, first I have to explain many terminology. What's a pure state, what's a mixed state, what's a coarse grain entropy, and what's a fine grain, and what's a polynomial entropy. So therefore, let's recall something about the basic about the quantum mechanics. So to explain this terminology. Some people may be too easy, but I think it's good to review some basics of quantum mechanics from quantum information aspect. So the entanglement. So let's entanglement in quantum mechanics. So it's so easy. so don't. Some people may get bored. Okay, quantum space is the psi is the in a Hilbert space. Given a Hilbert space, Kali H is the Hilbert space for me. Hilbert space. Psi I, and if you have an operator, so operator acts on psi I is something like O. Okay, maybe operator O of AI is acts on psi I. Okay, so this is in terms of so this is a psi I is called eigenstate. This is the eigenvalue. So this is well known. So this psi I is the orthonormal basis. Orthonormal basis of the Hilbert space for operator O. And then in that case, the operator can be written as the maybe the way I wrote is not okay. Maybe I call it I. So that this operator can be written AI psi I stands for OI. Okay, so that's how. So this is called spectral decomposition, or whatever, spectral decomposition. Okay, and then density matrix in the of the system can give you the okay. So density matrix system. Matrix of the system rho is written something like this: Pi psi I, where and this is kind of like a probability. Probability for the system has a states I, psi I. Then note that the psi I is different from I here. It's a different basis. Okay, so all can be written as the A1, A2, like this way. In terms of I basis, like this way. I basis. The psi I basis is different from this I basis. So here, density matrix mentioned that in the system, or physical system, has the probability Pi, who's the density matrix tells it that the system can have this state psi I with a probability Pi. So therefore, if you consider the expectation value of operator O, so we have something like this way. I, Pi, psi I, psi I, and psi I, like this way. So this can be just obtained by just trace of row operator. So O. Okay. So this is the how it works for the to evaluate the expectation value using density matrix. Okay. Fine. So I mean, if you want, I mean, you can just plug in to the. Okay, maybe I should mention J here to make the psi J J here. So you just plug this one into here. You just have like this way: I and J, Pj, psi J, and I square times AI. So that is the that is the execution value. So the pure state means that the system is has a pure state. Is in the pure state means that the row is just like this way. It's like this way. So this means that the quantum state or a quantum state psi with appear probability 1. Okay, so therefore rho square is equal to rho. That's the important property. Otherwise it's called the mixed state. So this is definition of pure state. This is called pure state. So okay. Pure state. Otherwise, if not, rho describe mixed state. So therefore, in particular, thermal radiation rho is written by 1 over z. Sum of n e to the beta e n. I think, sorry, is there any minus sign? No minus sign. Do you need? Beta is, of course, 1 over Boltzmann constant. I don't like Boltzmann constant. It's like this way. Do you need a minus sign? You need, right? You need, right? Minus sign like this. So therefore, of course, if you just multiply it, you get the rho square is of course something like a z square sum over n and then e to the minus 2 beta like this way en. If you just normalize. So therefore, of course, rho square is not equal to rho. So therefore, it's a mixed state. Mixed state. Fine. Yeah, of course, I assume that they like this way. En spectral decomposition, it's also normal. So therefore, delta and n. So if you assume this way. Okay. So it's a mixed state. So now I explained what's the meaning of pure and the mixed state. Okay. And to explain the page curve, we need to consider so-called entanglement of or entanglement of two systems. Suppose you have a two region in a space. You have a two region A, whatever, and say the complement is B. That is the space complement beam. This is also okay. So one subsystem and the other subsystem. It's not necessarily a subsystem is okay. Complement is okay. So something like this one is also okay. Anyway, so whichever you call it. Then if your total system is A, is the you have suppose the Hilbert space is decomposed like this. Okay, then I think we can just write down the psi of the system A, B is something like a Ci mu I A cross. It just have a tensor product. B like this way. I and mu. Okay, so that's so both are orthonormal. Orthonormal. In Hilbert space HA is the same thing, orthonormal. In Hilbert space HB, like this way. And you just can have the decomposition of this way. Okay. Fine. Fine, and then if you consider the operator which acts on both A and B system, to define the operator that only acts on A, so you need to take the sum of the, you need to take all the Hilbert space on the mu operator A with cup B with mu. So sum of mu in the HB. Okay. Sorry. So this is called trace of B like this. So this will give you the operator on operator acting on only on HA. Okay. That's quite natural. Okay, so that's and vice versa. If you want to construct. Okay. The reason why I just consider such a system is that I just want to consider the A is a black hole system, and B is the thermal radiation. So like this way. So one is the black hole system, the other is the system for thermal radiation. So we want to consider total system, and then looking at only one of the aspects does not give you the does not solve the information paradox. You have to consider a total system to solve the information paradox. That's why we need to entanglement is very important. Okay, and then state. So if you state psi A cup B is just like this way, tensor product of this way. Chi, this is called then it's called separable. Separable. So phi and chi are just a quantum state, single quantum state. So suppose HAB is a two-spin system, whatever, plus minus A and B. Both are two-spin system. Even if you write down psi is separable, I mean A and cup B is something like 1/2. Let's see. I'm lazy, so I will write down like this way. What was that? Like this way. So if you write down like this way, even if you write down like this way, this is indeed equal to 1/2 plus minus in A, and then cross plus minus in B, like this way. So the first first entry is A, and the other entry B, like this way. Okay, in B. So therefore, it's like each state look like like this way. So this guy look like this way. So this is the separable state. That's true. But if you write down the combination, it look like it's not separable. But if you write this one, it's actually purely single quantum state. This guy is also single quantum state. So therefore, this state is separable. So this state is separable. Okay, now on the other hand, so if not separable, otherwise, it's called entangled state. Otherwise, it's called entangled. So entangled one is the something like this one, psi e a cup b is equal to 1/2 plus and then 1/2 minus like this way. So this one you cannot write down the tensor product like this way. So this cannot be written something like this cannot be written something like a psi a cross whatever chi b. Okay? Chi b. So therefore it's entangled. Okay. And then, so therefore, so one can just write down something like psi a cup b is just written down like this way, square root pi I. So this is called Schmidt decomposition. This is the Schmidt decomposition. Schmidt decomposition. So you just pick the suitable orthonormal. Suitable orthonormal base is both A and B. So I sub A, I sub B is a suitable orthonormal suitable pair of the orthonormal bases. Orthonormal basis. Then one can just write down like this decomposition, and if you can find the pi is something like a 1, 0, 0. Anyway, so it's 0, 0. Then psi a cup b is the called separable. Is separable. Otherwise, entangled. Okay, entangled. Okay, so that's the what's the meaning of terminal separable entangled. Okay, so then when we look at the when we look at the in the homework, I think which is due this Sunday, I don't remember. So you have to show that the zero Minkowski vacuum is in fact, I don't remember, some coefficient and sum over n and the e to the minus beta en. En. Rough form is something like a right Rindel wedge cross left Rindel wedge, like this way. Rough form divided by whatever z or something like that, some number. You have to show like this way for the case of to see that Unruh effect really like how to say, this is V and U, and this is right Rindel wedge and left Rindel wedge. And then, in fact, the Minkowski vacuum is actually, so En is the orthonormal basis of this accelerating observer. What was that? Orthonormal accelerating observer, like this way. Is En is the, for accelerating observer, one can just have orthonormal basis, right and left. So one can just write down this one. So therefore, this is the really entangled state in terms of in terms of accelerating observer in right and left Rindel wedge. Even though vacuum is Minkowski vacuum is just how to say in terms of this how to say static observer in Minkowski's. So this one is the. In some sense, I mean, it's, you cannot define it. In Minkowski space, it's just a, what was that? I wrote somewhere. Yeah, I mean, it's in Minkowski space, it's not the, how to say, it's not decomposed like this way. Okay, it's not decomposed. Minkowski space is not decomposed to subsystem. But if you divide by two subsystems, Minkowski vacuum can be written in entangled state. That's what it means. Okay. So now we are talking about the density operator rho of A. Density operator rho of A is just a trace of B, and then rho A cap B. Okay. So this is the sum over I inside HP, and then I psi AB cap B, and then psi cap A. Okay, and then here I just plug this one into here, and what you get is something like a sum over both A and I, like this. Becomes so here I just plug this guy into here, then do the computation. So this part is B, this part is B. So since the I runs from, so you have to trace over all the Hilbert space in system B, outside of B. Okay, system B. Okay, so that's how you, so if you trace over all the other subsystem B, you can get the density matrix in the other subsystem A. Okay, so that's how you define the density matrix or rho A. Okay. So its immediate consequence is that the so immediate consequence, if the psi is separable, rho A is a pure state. It's immediate consequence actually. So immediate consequence is that the psi is the separable. Then rho A is the pure state. And psi, anyway, A cap B is the entangled. Then rho A is the mixed state. Okay, so therefore, I mean, Rindel observer, if you just how to say, trace over all the left wedge mode, and the density matrix on the right wedge is the really entangled, which is some radiation, which is consistent. Okay. Now, so we just define the so-called von Neumann entropy or entanglement entropy, whatever we call it. So, von Neumann or entanglement entropy is the von Neumann or entanglement entropy, whichever. And entropy P of this total subsystem SA is given by minus trace rho A log rho A, like this. Okay, fine. Any question at this moment? So let's do some simple computation for the one I wrote here. The entanglement entropy. Suppose this is the psi. Okay, so let's compute entanglement entropy of this guy. Do I do the correct? Sorry, I think I need a proper normalization to get the. Can I put the square root 2 over there? I want to put the square root 2. Okay, suppose let's consider SA for pure state, for instance. Okay, let's do the both. SA of the, so okay, let's compute, no, rho A, so let's compute rho A. Rho A for this guy, okay, for rho A for this guy is something like, seems like I might make mistake. It should be 1/2. And then plus minus A cross the same thing. Minus plus plus like this way. Okay. Do you agree with me? Is it okay? Do you understand? So I need to sum over all trace here. So here, did I erase already? So I have to do this one. So what I need to do is that the rho A is something, okay. Can I call it this one is the, can I call this the, I don't like this expression. Anyway, so this one I call it the alpha plus, psi alpha plus, is it okay? And psi alpha minus is like this way. Okay, is it okay? Is it okay? And then I just want to take a square root 2 of this one, square root 2. Then they should be the orthonormal. So then I think, so what we need to do is something like this one, right? Sum of plus minus b alpha plus psi, this one, and psi s alpha plus, right? Alpha plus minus, sorry, plus minus. Is it okay? And since we know that the this is alpha plus b, right? So since it's a pure, how to say? It's not pure. Separable state. We only see the plus state, right? We only, when you sum over b, so this psi only see plus state, okay, not minus state, because this guy is already alpha plus, not alpha minus. Therefore, this will give you the something like alpha plus and alpha plus in A. Okay, so which is this guy? Okay, is it okay? So as a matrix, this can be written like a 1/2 0. Okay, as a matrix. So this is alpha plus basis and alpha minus basis. And I don't like this 1/2. I think I want to have a 1. I don't know why I have a 1/2. Anyway, so after normalization, it should be 1. Yeah? Is it correct? I don't remember. Anyway. Huh? Normalized basis. So is this okay? No? No, okay. Square root 2, right? Square root 2. Square root 2. Square root 2. And the normalized is square root 2, square root 2. So yeah, I don't like that. This should be square root 2, right? I guess. Is it okay? Okay. So then this become 1. Okay, this become 1. Okay, this become 1. And if you compute entangled entropy, so the so it just SA is the how to say log 1 and plus times 0, right? So this is the entangled entropy. Is it okay? Log 1 is equal to what? 0? Is it 0, right? So therefore this is 0. So there is no entanglement. It should be. So that's how it works. So since it's a pure state, no, it's not pure. Separate state, yeah. Since it's separate state, log 1 is 0, and log here, if you just look at 1 times log 1 is 0, and 0 times log 0 should be 0. So therefore, if you add them up, you get 0. So there is no entanglement. So that's why it's called separable. Okay, let's do the computation here. Here, I think row A should be something like 1/2 plus, and then minus. Sorry. Minus in A. That you can easily see, right? So the plus and minus are the basis, complete orthogonal basis. So therefore, if you sum over plus in B system, you get this state. If you sum over minus, if you take a contraction with the B system, minus B system, you get this one. Okay? So therefore, as a matrix, it can be written like 1/2 or 1/2, 0, 0. And the entanglement entropy is something like a minus 1/2 log 1/2 times 2. Okay? So 1/2 log 1/2 and 1/2 log 1/2 from both sides, and this will give you 2. Is it correct? 2 log 2? Is it all log 2? Log 2. Is it okay? Log 2. So therefore it's non-zero. So it's non-zero. So therefore it's really entangled. Okay. So therefore it's non-zero means there's something in entangle and A, B. They talk to each other somehow. Okay, so that's the entangled entropy. Okay. So normal entropy. Okay, so that's, I need to properly write the lecture note. So as I mentioned, this week I didn't have time, so my lecture note have a full of typos, full of mistakes. Okay, so suppose we have row A is something like row A is something 1 over z sum over n e to the minus beta n e n and e n. Suppose like this way, you can write down like a thermal state, and then it's super easy to write down. So this is the essential Hamiltonian. So therefore, anyway. So, and then z is in fact equal to trace of A of e to the minus beta HB, HA, okay, HA, like this way. Then if you just do the normal entropy, SA is minus trace over A, row A, log rho A is in fact equal to beta and then HA plus log C. Okay, so this one can be written actually the e to the minus beta HA divided by Z. Okay, like this way. So that just take the plug this one into here, and then sum over rho A means that it just gives you beta times back expression value of rho A and log Z. Log Z come from here. Log Z come from here, and then of course this part is coming from this numerator. And then since if you take appropriate sign, it should be okay. Okay. So then this one is equal to beta times E minus F, which is the consistent with the entropy of the thermodynamic. So this, in this case, if you plug it, so this is thermodynamic thermal state. If you just consider thermal density matrix into the definition of this von Neumann entropy, you just get the correct. You just reproduce thermodynamic entropy. Thermodynamic entropy. Okay, so now for von Neumann entropy is kind of some kind of refinement. So that's why people call fine grade entropy. Grained entropy. Fine. And this has a lot of properties. So I'm not going to derive everything. I'm not going to derive. So there are lots of property. I'm not gonna. I mean, it's not so important to list everything. So if the composite system, A and the composite system A cup B is in a pure state, then SA should be equal to SB. So this is one property. Number two property is the psi A. Okay, this is already we look at is equal to is the separable, like this like this case separable. Then the SA is equal to 0, equal to SB. Okay. And then, yeah, so the log SA and SP are bounded by minimum. Sorry. What was that? Sorry, what I'm trying to talk about is what? Yeah, so the total system, von Neumann entropy, number 3, von Neumann entropy total system. So this is important, log of rho. This is has to be minimum of the dimension of the log of, okay, minimum of SA and SB. I think log of dimension of HA and log of dimension of HP. So this is most important property. So this is relevant. So this is most important in page curve. In page curve. This is most important. Important for us. Force. Okay. So this means that why this is important. So total how to say fundamental total system should be bounded by the log of dimension of the one subsystem. So therefore, if one of the systems shrinks to very tiny, the total system should be bounded in that Hilbert space. Okay? So that's the most important property of this von Neumann entropy. In total system of von Neumann entropy, it's bounded by the subsystem of the dimension of the Hilbert space. Okay. So therefore, one system is very shrink. If you consider the the Hilbert space of the one system is, shrinks to shrinks, then the total system should shrink. Okay. So therefore, it does not obey this usual thermodynamic entropy law. The second law of thermodynamic entropy. So this one is not relevant for fine grained entropy or for normal entropy. So that's the most important part. And then also strong subadditivity and so on. It's also important for other cases and so, but I'm not going to go into detail. Fine. Okay. Fine. And I need to talk about the fine grade and the coarse grade. And I told you the fine grade is really von Neumann entropy. Von Neumann entropy. And then the coarse grain entropy is, I mean, it's kind of complicated. So coarse, okay, let's give you the definition. Coarse grain entropy. What is the coarse grain entropy? So suppose a system is described by density matrix rho. Then suppose system is given by is described but then rho tilde. So suppose that for any set of any observable OI, rho tilde OI, so the expectation value is given by like this way. OI like this way. And then, so suppose any set of OI rho tilde, so this is another density matrix. Such that it obeys this property for any operator OI, then one can compute the von Neumann entropy of this rho tilde. Okay. And the coarse grained entropy is that the maximum of such operator rho tilde, which obeys this property, is the S coarse grained. Coarse grained operator entropy. So you just consider that any So bring like whatever density matrix one can create from this whatever Hilbert space, and then try to find the all density matrix which satisfy this property, and then take the maximum value of this von Neumann entropy. That is called the coarse-grained entropy. But it looks very complicated, but this coarse-grained entropy obeys. It's kind of like it's really so this is aligned with the thermodynamic entropy. Dynamic entropy. Thermodynamic entropy is aligned with the thermodynamic entropy. Because I mean in thermodynamics, all I is very small. I mean all I is very small, like a E or like a whatever. What else? Thermodynamics. We only consider the Hamiltonian or like a momentum and so on. Anyway, so the thermodynamics, so the OI, the number of OI is very small. So therefore, the possibility to rho tilde is very, very large. And you can take the rho tilde as this usual, the one I told you, e to the, whatever. E to the minus beta h, like this way. Since the number of OI is very small in the thermodynamics, so therefore one can just take rho tilde so that the S coarse graining agree with thermodynamic entropy. So in any case, so there is a property that the delta S coarse graining should be obeyed by second law of thermodynamics. Whereas the fine grained one does not obey this one. Does not obey this one. So that's the important part. And then by definition, so we only take maximum value of this fundamental entropy. By definition, S von Neumann entropy of the system, which is just obtained by just taking S von Neumann of rho, should be less than S coarse grain, less than or equal to the coarse grain entropy, coarse grain entropy. So by definition, okay. So that's the So that's the property of this. So now comes the page curve. So I explained the coarse and the fine grain entropy. So now comes the page curve. So why this S von Neumann and then time and the S radiation just keep increasing, and the S black hole is tau black hole. S black hole is to keep decreasing. So why does S radiation keep increasing? That's what I'm going to explain. So to do that, let's do the Naive estimate. So here we just consider the the shell black hole like this way, and then we consider the state we created by thermal radiation. So thermal radiation, so one is created by like this way. It's very schematic. So one is the outgoing one, so which I call it the B1, and the other quanta is called C1. That's what I call it. So then the system is the inside of horizon, and okay. So system is separated into 3 states. So I call it the psi m is a black hole state, and the times tensor with square root 2 is the plus. Okay, system is two systems. So suppose 2 systems like this way. So you just get uncanny. So these are system. If you consider And then since we cannot see, if you consider the, okay, so this is the outside and the falling inside. Okay, so this which means C1 and this is B1. Okay, suppose you have this. Anyway, plus means it's just how to say created. Minus can be understood a vacuum. So suppose you have a B1 plus and C1 plus. Plus means the B dagger acts on it. And the minus mean can be the vacuum. And as I did, here, if you just trace over of the M and the in of this this state, so this is psi, and then I think the fundamental entropy of outside is the same as before. The computation is log 2. Log 2, the one I already erased. The one I already erased computation. But if suppose there's another creation occurs, if time goes by, another creation occurs, C1 like this way, then the total system of the state is again entangled psi m cross square 1/2 plus plus and minus minus, and then this is number 1 cross, so square root 2 plus plus and then minus minus of how to say 2. So this is related to B1 and C1, and another is B2 plus C and C2. B2 another, so C2. Another particle after the later time. And if you compute fundamental entropy of this one of outside, this is 2 times log 2. Log 2. Because you have a 2 copy of this one. And then as time goes by, so lots of the particle is created. So therefore, so as the time goes by, so it just created the n times, okay, n times of square root 2. Then fundamental entropy out is n times log 2. So therefore, if you do the if you black hole just emit the thermal radiation, this fundamental entropy just keep growing, okay, by linearly in the number of particles. Okay, so that's why this S radiation will just increase by as the time goes by. Okay, so that's why so that's what the Hawking calculation tells us for. Okay. But now it comes a point that as I mentioned, so you have to consider S total should be considered S, what was that? Black hole plus S radiation. And if S is the coarse grain, it just obeys the thermodynamic law of the second thermodynamic law of entropy, thermodynamic law, so therefore it just keeps increasing. But on the other hand, if you consider von Neumann fine grade one, which is minus trace of rho log rho, is bounded by minimum of dim, log of dim, HA and log of dim HB. So now A means black hole, and B means the radiation. Okay. or A means inside a black hole, or B means the outside a black hole. So even if you just keep the S radiation is increasing, we know the black hole is decreasing, the black hole entropy decreasing. And we have to take a minimum of this Hilbert space. So therefore, once SA or SA or B is greater than S prime, or SA or SB, or whichever I call it. So therefore, the total entropy S rho log rho minus should be, roughly speaking, is much less than minimum of S and S prime. So this property tells us that if you use the fine-grained entropy, it should be taken at least a minimum. So this is become bigger, but the black hole will become entropy decreasing. But we should take for phonoma entropy, we should take at least less than minimum of the both two. So this is SA, can be understood SA, SB. The first time, SA is dominant, but SB is small. But we have to take, if the difference is very big, we have to take a minimum of the entropy, which is SB. Okay, so the total phonoma entropy should be less than SB. On the other hand, if as the time cross the page curve time, now SA is lower than SB. Okay, so therefore we have to take the phonoma entropy is bounded by SA. Okay, so therefore it should obey like this. So that's the argument of the page dip. Okay, fine. So that's why how you get the if you use the fine grained entropy, which is phonoma entropy in a total system, the entropy should obey this page curve. Okay, so that's what the page tells us. Okay. On the other hand, if you just do the coarse-grained entropy for the the Hawking calculation, you just keep growing. Okay. So therefore, you have to distinguish fine-grained and coarse-grained entropy. So that's the one thing you have to do. And then if you use the fine-grained entropy, it should obey like this. And the question is, can the black hole or quantum gravity can explain this page curve? So far, string theory does not explain this page curve yet. But the recent, I'm not going to go in detail. So I cited, at least it gives a citation, cite to the, there's a lecture by Daniel Hollow. It's called Israel lecture, I don't remember. And also the Surat Raju. So this is I forgot, lessons from information paradox. And recently this famous one, many people, sorry, I cannot write down all the names. So Hartman, Maldacena, I forgot. I'm very sorry. I cannot list everything. So it's written in 21 and something like that. There are lots of review and also information paradox. What's that? Oh my goodness. Polchinski in 17, 16, and this is 22 and so on. Anyway, there's lots of important progress has been done, and the review is given here. So I'm not the expert. I think Joanne knows better. If you try to seek in the Sudan, yeah. And then there is so-called by important progress by so-called Ireland. Oh, maybe this is not the one. Anyway, Ireland formula. Pennington and then some other these people did. so this is the Hawking diagram for black hole population. Anyway, so here if you take a slice of this Cauchy surface of the Schwarzschild evaporating black hole, so the thermal radiation is really coming from near horizon, so around here. So you have to distinguish the cause. You have to take the composition of the Cauchy surface with the thermal radiation part, the other part, okay? And then the other part, and in fact, so around here you will receive Hawking, people will receive Hawking radiation from the past, On the other hand, so this is people, I don't remember H radiation, but here you have a H island. So to get the complete information on what's going on, this red region, you have to take actually a complement of this Cauchy surface. So not only the outside region, but also the something inside. You have to consider here is the inside. So if you just consider that some entanglement of the state in its H island and the H radiation, if you take an entanglement of this H island and H radiation, one can reproduce so-called page curve. So that's the recent developed by, I don't know, 5 years ago, I don't remember, the proposed. And there are lots of development, I don't know, I don't follow. Anyway, so that's a rough idea, which I only know. But these, especially this guy, this one explained very well about this island formula and so on. Anyway, so if you write down the, I don't remember. So max is a minimum? Oh, I'm sorry. Maximum? No. Sorry, minimum. Most likely minimum. Anyway, it's better not to write in that case. A over 4 plus S. Okay, it's better not to write down island formula. I think I already forgot how to write. Anyway, so that's the idea, and then there's not only the black hole entropy, you have to take some complement. Anyway, so that's the. So to first part, this part is important, but second term there is some semi-classical. Subtle point of quantum gravity tell you that this part is important. H island become important. That will give you just the lower part of this page graph, the later part of the page graph. That's a proposal for the island formula. Okay, so that's I explained about what's the problem or information paradox. So let's take a break, and then I will talk about something about black hole perturbation. Okay, let's take a break. yeah. Now. I think just write down now minimum and then x of a over 4 plus s codimension to surface sigma x is the region bounded by x. Okay, so this is the island form, which, okay. Okay. So when is the last week of this course? Can you check? When the last day? This week or next week? Can you check the?
This week is 15th.
15?
Yeah.
So how many weeks do we have?
Yearly 16.
So the next week is included. Okay, I will teach. I'm glad to teach. Okay, shall we resume in that case? Okay, so then I will talk about. So some people mentioned that perturbation of black hole. Of black hole. In my case is Schwarzschild. Because my card is too complicated, and also I don't want to. Yeah. Since Kerr case I don't know, to be honest. Even in Schwarzschild case I'm not familiar. What is perturbation of black hole? Why is it important? Okay. So perturbation of black hole is very important because suppose that whatever black hole state is something like a potential is something like around here, and put the there's a potential whatever b and whatever parameter is here. Black hole is somehow here. Once you do the perturbation, and it can drop to the instability. That's the so therefore it's totally unclear that the black hole is stable under the perturbation. Perturbation you throw away or whatever matter and so on. Or anyway. So it's important to study since the astrophysical black hole is not the totally stationary, because there are lots of matter is moving and so on, but there is some infalling object and so on. So therefore it's not totally stable. So the question is what if you throw away the black hole to some matter to the black hole, whatever charged object and so on. What's going to happen is the important thing. In particular, so this one, the question is it's a stability is the important part. Also, but this perturbation will tell us that the important information of the black hole, more precisely, the contents. No, it's not content. Mass and also spin. Also charges. To determine the astrophysics physical black hole, to determine mass and spin, charge and so on. So perturbation is also very important. And also this gravitational wave. So the long time ago, I don't remember when. It was more than 5 years ago. No, I think more than 8 years ago. Or like almost 10 years ago. I guess LIGO detected the gravitational wave. Which is from the binary black hole merger. So the black hole perturbation theory will tell you that the very important information about gravitational waves, so-called quasi-normal mode. Or ring down. It's called phenomena. So ring down phenomena is so like suppose I hope if you just hammer something, it just creates some bell, but the sound will decrease as the time goes by. Okay, so therefore this vibration will just decay this sound. So that is called ring down phenomena. The same thing happens in the black hole. So once you do the black hole merger, So if you look at the LIGO one, so you have like this way and then like this way. And after black hole merger occurs, you have the like this way. So around this point, black hole merger occurs. After that, it just the gravitational wave just decays to this one. So this one will just decay. The amplitude will decay, and the frequency is somehow determined by this determined by perturbation of black hole. So this is called ring down phenomena. So that's exactly the same that once you like hammer the link and then it just creates sound, but after that, it just decay, right? So that's called ring down phenomenon. And this oscillation is actually has some frequency. It's called the quasi-normal mode. This oscillation is called quasi-normal mode. Quasi-normal it's not normal because it's decaying. There is some particular frequency you have, and then you just have to solve some equation, something called Schrödinger-like equation. I think d square psi dr square plus omega square minus br star psi equal to 0. And then I will derive this one, and this one psi is called is related to delta H mu nu. So the metric. So you have to since you start with the stationary or static black hole metric, which is Schwarzschild in my case, and you just take the perturbation of the metric like this way. So this is a total G mu nu, okay? And then this some model of the delta H mu nu obey this Schrödinger type equation, and that would describe so-called quasi-normal mode. Okay, so that's the. So this was the. It's called Ritchie-Wheeler. So one is called Ritchie-Wheeler. And also the other is what I'm sorry, I don't follow the Zarelli equation. I think this is the axial perturbation, and this is polar perturbation. I will explain what the axial polar means later. This equation and the potential will become like this way. Potential. This BR is something. It's this is R star is the, as you know, this tortoise coordinate of the Schwarzschild. And then, by the way, so this is a formula for island formula. Which I couldn't replace. Anyway, so I'm not going to explain this island formula, but anyway, if you want, you can take a look at these. It's kind of embarrassing, so let's erase this first. So this one, so let's give you some rough story, because it's better to motivate first the students why we consider this one. So the quasi-normal mode is this. So this is R star, R or whatever. Oh yeah. So let's consider first B. B is something like this one. So this is R and B of R, and this is 2m, and there is some 3.3m is a peak, and B takes the following, roughly like this way, like this way. So this is the, it's called Ricci-Wheeler potential, and then, so the psi will just, will be somehow obey this equation, and then there is an ingoing mode and outgoing mode. So at the infinity, you have an outgoing mode, going mode, and then here we have outgoing mode has the following potential: e to the psi is something e to the I omega t minus r star, and then ingoing. And as you know, so even you have a potential, there is something, the amplitude will down, but there is still, you can just, how to say, overcome this potential, and there is at the horizon, it becomes only ingoing. And the psi is something like e to the I omega t plus r star. Something like this one. It's ingoing mode. R star is the tortoise coordinate at the horizon. So of course it's a horizon. So and this psi is a perturbation of the matrix. So therefore it can be understood as a gravitational wave. Okay. So even gravitational wave also can only enter the horizon, but you cannot go outside. Of course, because it's black hole, so even speed of light you cannot escape. So the gravitational waves propagate the speed of light, but so at the horizon you have only ingoing, and then at the r goes to infinity, it's just outgoing. In the middle you have some complicated potential. But you have a mixture of the scattered mode and then ingoing mode and so on. So those are it's called quasi-normal mode. So the quasi-normal mode is the one which obeys this so-called whatever. It depends on Ricci-Wheeler or the Rayleigh equation, depending on which model you consider, and then which describe a perturbation metric, and which obeys some certain property at the asymptotical infinity. Asymptotical you have outgoing and ingoing. So at the horizon it becomes ingoing like this way. But in the middle it's more complicated. And then since this form is very look like Schrödinger equation, then what's going to happen around here is can be just obtain. This psi or wave function, which is the perturbation metric, can be obtained by WKB method. WKB method which appear in quantum mechanics, which is kind of like in Schwarzschild case, one can do the computation. If you are strong at the computation, for instance, Chandrasekhar did this computation actually. If you're super good at the calculation as like a Chandrasekhar, one can solve this wave equation around even this region, and that match with kind of like a beautiful match with numerical calculation. So those are the I'm going to talk about from now on, and I don't think I can cover everything today. So some part I will. So maybe I can derive this one and then continue next week. So that's the plan of this one. And then you mentioned. So this is called Ricci-Wheeler the Rayleigh equation. So for Schwarzschild, these are actually. So this one is 50 something. this one is done by 1957, kind of amazing. Unfortunately, the really question, do I have the, I don't have the original, I don't know when this was obtained, most likely 70s. 70s, and this kind of, again, this perturbation of the black hole is become important around the from 70s. After 70, of course, I mean, as you know, the 70, before 70, the Penrose and the Hawking proved that it's a singularity theorem, so black hole, existent black hole is almost people believe the existent black hole. After that, they start really solving this perturbation of black hole. So therefore, after 70s, this area become very, very rich. And then for Kerr case, the similar perturbation, the calculation was done by, it's called Tukhowsky. I think he's Russian. And his collaborator, it's called Zeldovich. Yeah, and Tukhowsky and so on. So but Kerr case is too complicated, and so I don't want to. I don't know the detail even first of all, and I don't want to write down the lots of calculation to derive the Tukhowsky mass equation. So only I focus on Schwarzschild case. Okay, so of course, for astrophysical application, the Kerr case is the most important, and also this gravitational wave from black hole motion is really, you have to do Kerr calculation, the calculation in the Kerr case, but I don't have ability to teach, and also it's too complicated. Let's avoid that. Okay. Fine. So let's consider linear perturbation of black hole. Any question at this moment about the motivation of that perturbation? Yeah. So So the standard textbook is this Chandrasekhar's, of course, the Chandrasekhar. Of this, I forgot, mathematical theory of black hole, something like that. I mean, if you open his book, I mean, it's full of huge, complicated calculations, impressive, but he has a guts to do that. He has ability to do that. I mean, Chandrasekhar is an amazing guy to do this kind of complicated calculation. Fine. So let's consider linear perturbation. Schwarzschild black hole. So what is this perturbation? As I mentioned, it's so the black hole metric is okay. You know, right? 2m over r dt square r square d omega 2 square. Okay, and then. So this is I call it the G0 mu. So it's a background metric. So the 0 means unperturbed one. Okay. So we know that the R0. So it's a vacuum equation. So this is the case. Okay. And then we perturb the metric. G0 of mu nu plus h mu nu. And the perturbations, I assume perturbation is very small. Okay. And here we still assume that it's an Einstein equation, vacuum equation. So here, so this is the perturbation, and this is total metric, perturbometric. I mean total metric. Okay, even total metric we assume the vacuum Einstein equation. So therefore, this should obey. So it should obey R mu nu equal to 0. So there's the vacuum Einstein equation. Einstein equation. And in principle, we just do the sum assumption. What we are going to do is impose some assumption on A mu nu and solve Einstein equation. That's what we are going to do. To derive this, whatever, Red-Wheeler or Zerelli equation. That's what we are going to do. To do that, so the R mu nu is R0 mu nu plus delta R mu nu. And since the unperturbable is 0, so therefore this one should be 0. Okay? So the perturbable Ricci tensor is 0. And the alternative way to explain this guy is something like a delta R mu nu minus it's just calculation. So this is what again? I mean it's just delta gamma beta mu nu is equal to 1/2 G alpha beta like this way. Okay. Fine, and then try to solve this equation. So we try to solve this equation. That's it. So idea is very simple. Okay, idea is very simple, but the important thing is that now here a Schwarzschild black hole is a spherical symmetric. Spherical symmetric. We have some spherical symmetric. So therefore, the metric dependent theta and phi is very simple, like just sphere. But once you perturb it, this spherical symmetry is broken. So therefore, this H can depend on the T R theta phi. H can depend on T R theta phi. So because I mean, you can throw away, it's like a rotating object, right? So it can have angular momentum. Okay, so perturbation can have angular momentum and so on. So therefore, this spherical symmetric is already this assumption no longer hold. That's the difficulty. No longer hold. Okay, no longer hold. Oh yeah. By the way, before I erased, unfortunately. So this stability is shown by Indian mathematician I'm very sorry, in 70s. I mean, Indian physicists in gravitational field is really amazing. This coming from Chandrasekhar and also Ray Chaudhuri and this guy. I'm very sorry, even though he's great, but I cannot write down his name. But the stability was shown by this Indian physicist. and often kind of like under-evaluated this kind of contribution. But I cited his paper, so you can take, you know. Okay. So to understand this angular dependence, or what was it? Oh yeah. So the angular dependence, we just need to do the decomposition of the spherical harmonic. So okay. Again, so we have to do the decomposition of mode. Decomposition mode can be achieved as follows. If you have a function, theta phi. So you have the sum of ALM of R, YLM, theta and phi, LM. So L is of course the total angular momentum. M is the eigenvalue for z-axis. So that's the and the YLM is that appear in the whatever. Even classical mechanics or quantum mechanics and so on. Okay, for vector, we can have a following the B alpha. For B alpha, one can just have the following. Can be for vector spin 1. This is spin 1. For spin 1, we have a following decomposition: LM. YB LM plus BLM YE LM. And this has the indices alpha. This has indices alpha. And then here you have this one is magnetic. And this is the electric. And similarly, if you have a spin 2, which is like a T mu nu of a stress energy tensor, this can be written as follows: a sum of ALM and Y is called X and Y. I use not the Y, somehow A. Okay. Anyway, so let's use A. And X LM theta phi, and then mu nu plus BLM, B polar. So this is polar and this theta phi, and the mu nu. So this is the spherical harmonics expansion for the mode for perturbation. So of course later I will use this one for H for perturbation metric. But let me explain what does this axial and the polar mean. Okay, so to explain axial and polar, you have to consider parity transformation. So parity transformation. So to define what's the meaning of axial and polar, so you have to consider parity transformation. Which is just a F whatever LM theta and phi mu nu is mapped to F or M pi minus theta and pi plus theta, pi plus phi of this one and the mu nu. So this is the parity transformation one can consider. I don't know why I put the tilde on the, anyways. Oh yeah, tilde. And F tilde LM is just a -1 to the L F mu nu. then this is called a polar, spherical, or even. And minus 1 to the L plus 1 F mu nu. No, not mu nu, sorry. Well, it's not the mu nu. Lm. Okay, somehow, okay, I'm stupid. Lm. So then it's called the odd or axa. So this is the case. So here, so when you do the expansion, here, this ALM obey under the parity is you have a minus 1 to the L plus 1. On the parity transformation, this ALMs obey this rule. Okay, obey this rule. On the other hand, this BLM obey the upper rule, so the minus 1 to the even L instead of L plus 1. So that's the difference between axa and the polar. And if you pick only odd case or axa case, so if you turn off this one, so if you only focus this one, you get the Regge, Wheeler equation. And if you consider this one is called, what was that? The Zerilli equation. So that's the difference. So due to historical reason, so let's consider this axa one or odd one. So just do this decomposition and then plug this one and then solve the Einstein equation. That's what we are going to do. Okay. So we just perturb the metric as follows. So here H00. So let's focus on this odd case or axial case. Axial odd. So to perturb metric before the so the H00. So this is the assumption you will get. H0I is something like a H0 function T of R, and then the following equation. I mean, just spherical decomposition. The time component is always, we assume that I don't want to write them. Okay. So minus sum over partial phi YLM sine theta. So sine theta and sum over partial theta YLM. So this is the this is R component, theta component, and phi component is the for H0. So we will do this kind of decomposition of the spherical harmonics. H1 TR is equal to sum E hat 1 what was that? IJ, and then plus H2 TR E hat 2 IJ. So this is the spherical harmonic decomposition of like this way, and then here this guy is polar, and this guy is axial. So axial. So therefore, so suppose H2 0, so this guy is equal to 0 in the case of axon. And H1 is, E1 is the E1 hat IJ is of course, it's just a spherical decomposition is assumed. E1, 2 IJ and the Ln. So Ln. So this is the assumed. So there is some, it can be written as the as a spherical decomposition like this. But if you do this assumption, let's see. So this guy is equal to 0. The H axial can be simplified as follows. I want to keep this one. So maybe keep this equation. So this, if you take H2 goes to 0, so this H mu, the axial can be written in the very simple form. So this 3 by 3 is all 0, 0, 0, 0, and everything the other is 0, H0, H1, 0, and then 0, 0, H1, and H0. Okay, so that's the form we will get. Most likely the way I wrote is what part times sine theta partial theta PL cos theta e to the I and phi. So it's okay. I think it's too simplified. I don't know how to. Sorry. So this step, to be honest, I don't know. Let me accept this fact. Maybe next time I will explain why this is the case. I don't know why this way has become so simple like this way. And of course, this is Legendre polynomial. To be honest, I don't know why it becomes so simple. Infinitesimal coordinate translation. Okay, anyway, so let's first accept this fact and then plug this one into this equation. This equation.
How you got the values for H0i?
H0i can be obtained by solving this equation. So this decomposition. This decomposition is the spherical decomposition. Will give you some natural way of assigning that. I don't know why, to be honest. Sorry, I don't know. There is some natural way of assigning spherical harmonics to the metric. So that is this ALM. Okay, so sorry, but I don't know, to be honest, the answer to your question. And but if you use this metric, one can just solve this. So if you plug this one into the perturbed Einstein equation, one can just obtain the following equation. the following set of equation. Partial square q, partial square t minus partial square q, and partial r star square plus 1 minus 2m over r, l plus 1 r square minus 6m over r cube, and the q equal to 0, and then del h 0 divided by del t is equal to del r star q, where r star is the total exponent, plus 2m r over 2m minus 1. Okay, so that's the equation you will get for h0, and then seems like h1 also receives the similar equation. So here you have a h0 and h1, and then h1 also obeys a similar equation. So you have to solve this, how to say, the set of differential equation to get this perturbation. Okay, perturbation.
And
So
Q is
Q is the Q. If you solve this one, you can have the Q. You plug into here, that will give you H0.
yeah. What is Q?
The Q is the. I mean, if you to solve H0, you just introduce the so-called some other functions that satisfy this equation. Yeah. Okay, so this is the so-called. This is called the Recce-Wheeler equation. Recce-Wheeler equation. And this is called potential B of R star. B of R. Okay. B of R. To obtain. Okay, so then, so one can just obtain the this. So this the potential is exactly the one I wrote before. So this potential B of R is the maximum is 3.3. The mass, and then it starts with, of course, it can just, if you look at this form of potential, when R equal to 2m, this time is 0. So therefore B of R is 0. But once you go to R goes to infinity, this term becomes 0. So therefore R goes to infinity becomes the 0. So therefore it becomes something like this way. And asymptotically it just decay as R to the minus 2. Just like this way, or R, like this way. So that's how it behaves. So maximum like this. So that's the how this potential look like. Okay, and so asymptotically regime, so you can just ignore this one. So therefore, partial t. Sorry, let me square q minus partial square q partial r star square acts on equal to 0. That's what you need to solve asymptotically. So when r goes to infinity. So therefore, it's just a wave equation for wave equation so that one can solve the equation. So this has the asymptotically e to the some e to the something like a I omega t, and then here what's going to happen? Yeah, plus minus r star, like this way. We'll solve this equation asymptotically. You can get this equation. So there is another way to solve this equation by just solving. To get this equation, that is I'm going to explain. Is that I think that will answer your question. That will answer. So so this is the spherical harmonic decomposition. I just want to explain what's the meaning of axis and so on. But the other way to explain is as follows. So suppose we have the following form. The metric ds squared is equal to e to the 2 nu dt squared minus e to the 2 zeta. So this is Chandrasekhar way. d phi minus capital omega dt minus q1 dr minus q2 d theta square minus e to the 2 mu 1 dr square minus e to the 2 mu 2 d theta square. So this part is not written in the lecture note, so which I haven't typed it yet. E to the 2 mu is equal to e to the 2. I mean, it's just perturbation, so it's equal to 1 minus 2m over r. And then, what else? E to the mu 2 is equal to r, and e to the theta is equal to r sine theta. When omega is equal to q1 is equal to q2 equal to 0. Okay. So to get the Schwarzschild metric, we have to get the Schwarzschild metric, you have to impose this one, Schwarzschild black hole. So if you assign omega equal to 0, q1 equal to 0, q2 equal to 0, and then you just assign the specific value of the, for instance, e to the 2 mu 1 should be this inverse, and also e to the 2 nu should be this guy, and then these are the exactly that appear in the spherical metric of S2. Okay. So now we just metric perturb. This is no longer 0. This is no longer 0. Now we assume these are no longer 0. These are no longer 0, but very small. And then this parameter also will be modified a little bit. Okay. And then solve this equation. Okay. And to solve Einstein equation, so let's do that. So this is another way to derive a Ricci-Wheeler equation, which is kind of complicated, but I think this is more intuitive, more direct way of doing that. So delta r mu nu equal to 0, and we just look at the delta r phi r equal to 0. Delta r phi theta equal to 0 will give you the following equation. E to the 3 theta plus nu minus mu 1 minus mu 2 q12, and the derivative by 2 is equal to e to the 3 theta minus nu plus mu 2 minus mu 1 q01 derivative 0, where the Q12 is given by Q to the 1, 2, Q 2, 1. I mean, dot indices mean derivative. Q0 I. I mean, it's just so complicated, but you have to write down and 0 like this way. Okay, so this is the equation. And also, there is another equation one can obtain. So, if you change this one to 1, the same power show up, but the index becomes 0, 2, and 0. Okay, so that's the Chandrasekhar way of writing that. And then here there is a here there is a minus sign for uppercase, but this is plus sign in lowercase. Yeah, but two equations you will get. So now we just need to solve the equation for this. So what I use is that the notation is that the gamma alpha dot beta means the gamma alpha divided by ddx beta. So that's the notation over there. And if you use the new variable, this is anyway. So if you look at the Chandrasekhar book, it always like this way. It's lots of like a new variable like this way, bunch of variable, and then write down. So this equation, where copper is given by r squared minus 2mr, like this way. And then, so this equation, these two equations we simplify as follows. 1 over r to the fourth, so r to the fourth sine cube theta del q del theta equal to minus omega 1 minus q10 dot 0, like this way. And the other one is something like this way. And this become plus, and this become delta r, del r. Okay, this become delta r, and omega dot 2 minus q 20. It's the same. This means same. Anyway, so like this way. The other become like this way. Cube theta like this way. Okay. And we just consider that this guy has a frequency. Q is frequency of e to the I omega t. Omega t. So 0 is time derivative here. So therefore, that will simplify the equation. I think where can I write down the? I mean, that's why it becomes really complicated. Okay, maybe I can erase here. I can erase here and write down. Anyway, so this is the equation with I already forgot. So this is the equation for del r equal to 0, some component here. And if you just introduce notation, the two equations become like this way. And furthermore, if you just assume q is proportional to e to the omega t dependent, then this equation becomes like this way. R to the, maybe I can just write down over there. So if you just assume this one, this dependence becomes like this way. So I omega minus omega square q1 and then plus I omega dot 2 plus omega square q2. Okay. Okay, now we can just eliminate this omega. So this is a Chandrasekhar way of doing that. So you can eliminate this omega by further divided by this 2 here, derivative 2 here, derivative 1 here. Then omit the equation for omega. So then I can erase here. Then you get the equation for Q. Which is something like this one. R to the 4th, del R, kappa of R to the 4, del Q del R, plus sine cube theta. Anyway, so this one you have to do the calculation. Sine cube theta, del Q del theta. Okay, del Q del theta. And what was that? Plus omega to the square R4 to the kappa of Q equal to 0. Okay, so now this is the equation. It's a boring calculation, but it has to do it. Then now it's very look like this one, right? It look like this way. So then here I assume the t derivative is give you omega square minus omega square here, but the other part is very look like this way. If you assume theta and phi dependence is spherical harmonics. So therefore, Q is really coming from Q12 sine cube theta. Q12 is given here, and Q1 after Q12 is just somehow perturbation of the metric coming from here, in here. So that's the origin of capital Q, actually. Capital Q here. Okay. Now. So we just assume the spherical harmonics dependence of Q. What should I write? Maybe I will write here. Fine. So now assume the Q of R theta is R of R, and you just decompose like this way. Capital theta of theta. Then this equation become like this way. So the I mean theta part is not important, so I just write down like this way. dr kappa R to the 4th, d capital R, dr. Yeah, that's why this perturbation calculation is horrendous, but Chandrasekhar is brave enough to do that. Plus omega square capital R equal to 0. Okay, then if you introduce tortoise coordinate ddr sine, its time is over, sorry. Kappa over R square ddr. So therefore, this part can be written as ddr star, and this can be written as follows: d square psi dr star square plus omega square psi is equal to b psi, like this way. And b is exactly written over there. And then psi is in fact psi of r is equal to capital R. So anyway, so this is a change of variable you have to new function you have to introduce, and this is exactly the one is coming over there. Anyway, so that's the calculation one can do from the perturbation of the metric. So one way, I don't know how to do the step, but the other way is the Chandrasekhar way, which I haven't written down yet. But anyway, so this is another way to derive it. If you assume the time dependence is like e to the I omega t. Anyway, so then if you solve this one, you will get the quasi-normal mode, but that is next time. And then the step I couldn't explain, I will explain next time. Okay, let's stop here. Okay. Yeah, I will write down all the calculations I showed today in the next week.